Hello, a great welcome to Idea Statica tutorial. Myself Jarajan P. Here I will show you how to model, design and check a structural steel joint. The example of a beam-to-beam end plate bolted shear connection is considered. The sketch showing the connection details to be modeled and analyzed in Idea Statica is shown here. So let us now proceed to model this connection in Idea Statica. So let me click the connection button in Idea Statica. So here you'll find the connection wizard. So the connection wizard will help the designers to model their joints very effectively and in the shortest possible time. So here I have two options of modeling this joint. First thing, for example, in the class I can choose a beam-to-beam connection, and in the geometry I can choose a rolled beam-to-beam connection. And for example, here I can go for a shear connection using the end plate. So one option is that I choose straight away my connection here. That's a beam-to-beam connection using an end plate with anchor bolts, and I can start modifying this connection. Another way is that I can start from a blank project. So as it's a tutorial, I think it is better that I start with a blank project, and then before starting this project I need to enter some important details through the parameters window. I'll just enter the project's name. For example, here I will write down the polymerization plant. And here I will write down the rack beam. And here you can select the steel grade that is finalized for the project. Here I have chosen S355, and the bolt assembly I have taken the M20 bolts of class 8.8, and the concrete grade for the project is fixed at C25, C13. And finally you can select the most important one, that the design code to be used for the analysis and sizing of the joint. So Idea Statica supports a number of international codes, namely the European codes, AASC, that's American codes, then the Chinese codes, then Australian codes, the Indian codes of practice using IS 800, and Hong Kong codes, and many other codes. And in AASC, it supports both the AST approaches as well as the LRFD approach. So let us start from a blank project. So I will, with the input of all these parameters, let me press the create project button. So as you can see, this is the graphic window empty because we started from a blank project. So now we need to populate this window with the joint model, and this can be easily done using the three buttons. These are the most important buttons. That is, you can add members, you can add the loads, and you can start loading any kind of member operations, or popularly known as the manufacturing operations. So let us start adding the members. Okay, so I will press plus button. So here I will choose the rolled sections, and in the rolled sections, straight away by default, as I am using the European code, it started with the IP profile. So what we can do is we can start with the all. So in this project I have used the UB sections. So let us start going to the UB. Yes, I have chosen the UB here, and now I need to fix the main beam connection. Okay, so let me start filling the details. So as far as the beam is concerned, we have the UB, that is UB 610229. So let us just select it. Yes, UB 610 140. Okay, so fine. So here, once you choose this beam section for one member, that is a UB 610 by 229 by 140. The sketch displays you the various geometrical dimensions, such as the overall depth, the flange dimensions, the flange thickness, as well as the web thickness. So okay, fine. Now you will find that one member is automatically modeled here. Okay, so now using this side screen, it is possible for us to edit all the required parameters. Now I want that this main member, it's a continuous one, so I will mark it as a continuous. So go back to this perspective view. So this is the representation of a continuous member, and here, as you can see, all the rotations associated with the members are given here. For example, the member orientations with respect to the various axes are specified through the alpha, beta and gamma parameters. And for this member M1, we will set it as a 0, 0, 0, and all the offsets will be 0, and the alignment we will select it as the in node mode. And I will choose the model so that its supports can resist all the 6 force components. Okay, that is the Vx, Vy, Vz, and Mx, My, and Mz. And the forces, I will choose it at the node. Okay, so my member M1 is modeled. Now let me go for the modeling of the next member. That is, I will again press. So let me just add a new member. Yes, this is also a rolled section. And as usual, what I will do is that I will go for all, and then we will choose the UB section. Okay, UB is chosen, and the UB I will choose the required model. So for M2 I will choose UB 533210, UB 533210 by 92. Okay, so you can see that all the details of the section are given here. So press OK. Now here you will find that the member M2 is almost in alignment with the member M1. It's all because we did not model, okay, the orientation of this member axis properly. So what we'll do is that first, this is not a continuous member. This supported member, okay, will be chosen as an ended member. Okay, and then it is important that we specify the orientation through the what we call as the beta angle. So I'll choose the beta as minus 90 in this case. Okay, and then it is also important that we choose a particular offset for this member. Before talking about the offset, I just want to show you the model type here. Here I will, as my member is taking only the tension and the shear forces plus the moment in one plane, I'll choose my NVZMY category. Okay, and the forces, I assume that the forces are being applied directly in the bolts. And now here, before talking about the offset EZ to be applied to the model, let me just zoom it. Before that, okay, now let me just look from one angle. So look here you will find that, just a minute. Okay, now look here you will find that the TOS, that's the top of steel for the two members, are different, because in Idea Statica the member center lines are kept the same. So it means that the member M2 need to be shifted up so that the TOS for the two members will match. So what I will do is that I will enter this offset, the distance through which the member to be shifted upwards through the offset EZ parameters, and for this the calculated dimensions seems to be 42, so I will mark it as 42 mm. 42. Okay, now you will find that the TOS is matching for both M1 and M2 members. So we have modeled the two members. Now it is important that we start modeling, okay, the notches, because we find that it is a connection between the two beams. So obviously we need to make some cutouts in the flanges of the beam M2, as also we need to make some cutouts in the web also. So the operation of creating the cutouts in the beams can be furnished through the addition of the manufacturing operations. So after this, so we have modeled the two members M1 and M2 properly, so they are shown here. And now it is important that we start, okay, incorporating the cutouts, okay, in the member M2, which covers both the flange as well as the web cutouts through the manufacturing operations. So we just add operations. So in the operation, what we do is that we select the opening notch, okay, because we want to make a cutout, okay. And as you can see right now, this is being made in the member M1, okay. So this by default it is taken through the member M1. It has created an opening, but we don't want an opening. We rather want a notch to be created in member M2. So what we do is that we change this. We want the cross section part as we want a cut to be made in the M1 M2 top flange. So M2 top flange, okay. And in the shape, go and select the notch. So we have selected the notch, and the location we want it at the front, and select the cut to be made. So based on the flange dimension of the member M2, I have taken the width of the notch as 125, and the depth of the notch is taken as 210. So this is all these dimensions are fixed based on the dimensions of the flange of M2, and also based on the dimensions of the M1. So here we need not have to incorporate in a rounding radius. So we have created now a small cutout or a small notch in the flange. So let me just zoom it for you. So here you will find that a small notch, yes, a small cutout is already made in the flange of M2. Okay, so now it is important that we create a small notch in the member M2. Okay, so we have created a notch in flange. Now let us go for creating a notch in the web. So let us start adding another member operation. So it's again the same opening. So what we do is that we require it to be made in the member M2 web. So select M2 web, and obviously the shape will be a notch. So I will choose this as the notch, and let us start making the dimensions. So this is regarding the notch to be made in the web. So the corresponding dimensions would be, so M2 web 1 notch, and this will be obviously should be made in the rear. So you can have it in the rear, and depending upon the notch to be made, obviously it depends upon the flange width. So I will select it as 125 based on the flange width, and the depth of the notch is 50 mm, and I will keep a small for upping to a small rounding radius, that is let me say it's a 20 mm. Okay, so that is done. So now let me show you the model. So this is let me just zoom it once again. So let us rotate the model. Yes, so you'll find that, see, look here. So an opening is already made in the flange, and here you will find that a notch along with a curved root is made in the web of M2, and this was possible by the addition of two manufacturing operations. Now we need to add one more operation, that's a manufacturing operation, to include the end plate, because as already explained in the beginning, our connection is made by means of an end plate connected to the anchor bolts. So let us start adding an operation to insert the plate. Okay, here you will find that there's an end plate beam to beam. Okay, so I will press it, and here it is 8.8 M20 bolts will be used. So okay, fine. So as you can see, you'll find an end plate that is already generated for using the bolts. Now we need to adjust the top of the anchor plate, the bottom of the plate, and also we need to position or correctly align the bolt positions, and this can be easily done by pressing the EP1 button and then adjusting all the parameters. So let us start adjusting the positions of the various parameters. So obviously the end plate it is made in M2, okay, and it has to be connected to M1, okay, the member M1, and the grade of this plate, we'll select it as, we can add it, we can let us select it as a S275. So this is a S275, okay, S275, and then the thickness we'll choose it as 12 mm, and the connection type, it is a bolted. You can also have a welded one, so here I will choose a bolted one, and this is to profile. And now first of all, here we have the two parameters, one to adjust the dimensions of the end plate, and the second one is to adjust the positions of the bolts. So here we will adjust the positions. Remember, here I have taken to profile. To profile means the position of the end plate, it will be adjusted based on the edges of the profile. That's the edges of the profile of M2. So that means the top edge of M2, the left and the right edges of the M2 profile will be the references for fixing the dimensions. So accordingly, let me fix it as -50, -50, so that my edge of this end plate, it will be 50 mm below the top of M2, and the left and the right I will keep it as 0 here, and the bottom one I will keep it as -53. -53 indicates that my bottom of this plate will be 53 mm from the top of member, bottom of member M2, okay, and I don't require any backing plate here. Now let me position again all my anchor bolts based on the various dimensions. So here M28.8 I want, so here I will position the top layers first. So here I have put it as -90, -70, because we have got 6 bolts, -70, then another -70, and then -70, then we have got -70. Also we have one more row, -70. So the left layers I will keep it as, here it is -35, -35, and the bottom layers, because I have mentioned all the bolts through the top layers, so I need not to mention anything for the bottom layer. And the right layers, again keep it as a -35, -35, okay. So shear plane in the thread that is chosen, and now as you can see, this is basically a web to plate connection, so we need to mention the welds associated with the web. So here let me choose it as 6 mm, 6 mm fillet welds on both sides, okay. Let me just keep it as a 6 mm, okay, fine. So it does mean that our generation of the model is complete. So let me just quickly rotate it. So as you can see that this is Idea Statica will provide you all the dimensions associated with the bolts are given in the model, and all the positions are indicated. You can cross check it before going for the analysis, and please see that all the parts, all the components of this model are in perfect contact. And okay, so we have perspective. So now let me just input the load effects. So I will add the load. So in this case, as we know, we need to input only the loads at the ends of the member M2. So I have the M2 end. So this design will be done only for a VZ, that's a shear in the Z direction, -550 Newton, okay. So now we have added all the members, all the manufacturing operations, and the load effects. Now we are ready to go for the analysis. So this is our model. So let us press the calculate button to carry out the various checks. So the analysis result is presented here on the left side. So we find that the analysis is performed 100% for the applied loads, and all the components are well within the limits. And as you can see that the plates are the maximum strain is 0.1%, much less than 5%, and the bolts it's stressed to only up to 58.2%, and the welds is 7.4%. Now, to see the distribution of the stresses and strains, go to the check button. So you can check for the plastic strain. So here you will find the distribution of the plastic strain in the various members. So obviously we expect a larger strain levels in the zone where we made the notch. So here you will find that there is a concentration of strains because it's a weak part, okay, and the strains are somewhere of the order of say 0.1%. That is not a big issue. And we can also see the stress distribution. So let us press the equivalent stress. So we'll find the stress distribution in the various parts. Here as indicated, we can see that the maximum value of the stress is reached to 275 MPa in certain parts of the connected members. Now we can also see the various bolt forces. So by pressing the bolt force button, and you can also get a mesh view. Okay, so this is a mesh view already. So, and the summary of the results for the various components are presented on the side menu. For example, you can quickly see the verification for the various plate components, and please see that the plates means it also includes all the bottom flange checks, all the web checks for the connected members. So here you will find that M1 bottom flange 1 and M1 web 1. Okay, so also you will find that the main end plate component EP1, and similarly you can also see the results for the bolts. So just below you will find the distribution of the stresses in the bolts as well as in the plate, and here you will find a press button wherein you can also see a summary of the checks being carried out. So I will just press it. So here you will find that a brief summary of the bolt check is provided. That is basically carried out for the tension, but in this case we know that the critical force that will govern the bolts will be the shear. Okay, then also you can get the check in the welds. And now at the end of the analysis verification, and after confirming that all the results are in line with our expectations, we can go for generating the reports. So this is the reports, and here there are many options available for the generation of the report. You can have a brief, okay, brief one, okay. So you can have a one-page report. This is a very brief report of the calculation or the analysis results, and you can have a detailed one. You can press the detailed button. Okay, so this is all about. So here you will find all the input parameters. For example, here you will find the material summary. Here you will find out the member dimensions. These are the members, and the connection geometry. Here you will find, and all the load effects that are applied on the members are shown here. For example, here is the minus 550 kilonewton that is applied on the member. And also you will find out all the code checks performed, a summary of all the code checks performed here, right? Please remember that all the checks are being performed as per the UEC3, and you will also find the distribution of the plastic strains as shown here, the distribution of the stresses in the various components of the model, and also you will find the forces, for example, the shear forces, the tensile forces, and the utilities, and the final status check results for the bolt components. So, and if you want to include much more elaborate one, for example, if you are interested in adding some formula to the calculation report, you can press here. Okay, you can add the formulas into the report. Currently that is masked off, and you can also ask for the explanations, and you can also change the adjust the colors for various components in the picture. So that's all about. So thanks a lot. So please subscribe to the channel, because we will be loading much more new tutorials in the website, and that includes the moment connections, various other types of shear connections, and also many complex connections like the bracing connections. So that's all. So thanks a lot. Have a nice day.